Okay, welcome back to class, everyone. First, let me start off by apologizing. You may notice my voice is a little weird today. I got what my kid had. So I'm on the mend though. I'm feeling great. Any other day, I would complain about how I felt today, but compared to the last 2 days I've had, it's amazing how good I feel. So, bear with me as we go through class. You can make fun of me if you want. It doesn't really matter to me. But that's the situation, so you're not curious why I sound different. If I sound different. To me, I sound different. I don't know about all of you. So, did everyone have a good weekend? Yeah? Fun and exciting things? Okay, good. The weather's gotten cold on us, so, yeah, cold, I would say. There you go, wear your jackets and so forth, so you don't get sick, like me. See how I did that? All right. Last time in class, we were talking about dot diagrams. And doing dot diagrams of various compounds and then talking about the names of them and so forth. Today what we're going to do is we're going to continue on that train of thought and we're going to start using the dot diagrams to predict shapes. So before we get into that, that's what the slide there is about, is predicting shapes and so forth. A couple of announcements. First one being that the clipping 3 is due next week. Oh wait, no, it's due tomorrow, or next class. So make sure that you have done that and looked at it before class in case you're called upon to discuss what your topic was and so forth. I think we should have the gist of it by now. Any questions about that? I opened up a spot to submit your clipping online yesterday, so that's there for you as well, just in your normal clipping folder.
And then the extra credit is due.
When would you like it due?
I just forgot it at home. I was just going to submit it via Blackboard.
Okay, it's due today, but
I'll send it via Blackboard.
what?
Who make it be like nothing?
Let's have a class vote. See how many people in class like you. No. I don't care at all if you guys haven't figured this out at this point. The reason why I give work and so forth, there's really 2 reasons why I give homework. I personally don't care if you do it or not. The first one is so that you guys can get credit for things outside of exams. If this course was only graded on exams, I feel very badly about that because it's not a majors course. And I want you guys to have opportunities to get points and so forth outside of that. And then the second reason is just so you can see the relevance with things like clippings and get practice. So that's why we do homeworks. And that's why I don't really have hard deadlines for things, because I don't want to keep track of them, number 1. And then number 2, say you can't get it done by today, but you can do it in the next few days, that doesn't decrease your learning experience from actually doing it. So that's the reason why I don't really care that much. Yeah.
With our idea for our paper,
Yeah.
I think it's also Thursday.
Yep.
I didn't look at the syllabus recently. What would do you want something in hard writing as far as like a?
Yeah, so this is the other thing on my list of announcements is the topic paper. Due this week is your idea for it, and what that is literally just your idea. You can write it down on a piece of paper, you can tear a piece of paper off, you can use a Post-it, I don't care. You can send me an email, anything you want. In the end, you don't get credit for it, but I would like to get your idea for the topic paper just to make sure that it works for the course. I've never turned down someone's topic because I don't like it, but I have taken topics and narrowed it down. So the requirements for the topic paper is 3 to 6 pages, double spaced. If you want to write it single spaced, you can do 1.5, I don't care, to 3, whatever it is. But that's not really all that much text involved. I know it seems like a lot when you're a student and so forth, but sometimes students turn in ideas like alternative energy. In 3 pages, you could literally just list all the different types of alternative energy on this earth, and that would give you the 3 pages. That's not what I'm looking for. I'm looking for a little bit of depth. So the only time I've ever adjusted people's ideas is to like narrow them down. So if you say alternative energy, I'll say, well, choose one form of alternative energy so that you can write a little bit about that form instead of just listing the name of it or something. Medicine, medical interactions is another one I get from time to time. Look at one type of medicine or one drug for policy or whatever it is you want to do there. So the only time I really do anything with the ideas is kind of to help you out and narrow them down a little bit so you're not researching a huge, huge topic. But really it can be anything that you're interested in. Please choose something you're interested in, just for your own sanity. And you have to be able to tie chemistry to it some way. Now, throughout the class, I've been going on and on about how chemistry is tied to everything, so that doesn't really narrow it down at all. It can be persuasive where you're trying to prove an argument. So for example, some of them I've had there was drug policy, pro and con against laws and so forth, or treatment approaches. Evolution is one I always bring up. This is a good example because one of the best topic papers I've ever gotten in this class was an evolution paper, and it was completely against my views. So you don't have to choose a topic that you agree with me with. I don't care about that at all because they're your opinions and so forth if you're trying to make a persuasive argument. But you do have to actually present fact in a scientific way in some form, okay, and tie it to chemistry. So the student did a really, really good job on evolution, talking about, I forget what, anti-evolution, I don't know what that's called these days. And the scientific experiments that he thought showed the various forms of that. So he did a good job on the paper, I just happened to completely disagree with everything he wrote. And that's fine. So don't worry about tailoring your idea to me in any way, shape, or form. The other type of papers that I get is perfectly fine are informative, where you just choose a subject and you talk about it. Could really be anything. See, I had one once on different types of strings used on guitars. There are different types of strings used on guitars apparently, for different sounds and so forth. I have a lot of students in here that are on the golf team for some reason. I'm not even sure how many people are on the golf team. We have a golf team though, I know now. And I quite often get the chemistry at different types of golf balls, like they bounce differently and things like that. So if that's your thing, great, go for it. It really could just be anything. But choose something you're interested in so you're researching something you actually care about and not just climate change. If you don't care about climate change at all, don't do that. Does that make sense? Okay, the other requirement is that you need to have 3 print sources for your topic paper, and these have to be in print somewhere in the world. You don't physically have to hold the print version, but it has to be in print somewhere. So if you have an electronic version of an encyclopedia, that's perfectly fine. That would count as a print source. The reason why I say that is because generally print sources are, this is not always true by any means, but generally they're a little bit better in terms of research and backing them up with facts and so forth than just your ordinary internet blog or something like that. You can have as many resources or references as you want, but 3 of them need to be print. Because literally on the internet you can find anything you want. A prime example of this, I did this a few years ago. I was trying to come up with the most ridiculous thing to show that you could prove anything on the internet. And you guys are aware of Smurfs, right? You know what Smurfs are, the little blue creatures? Yep. We're all aware. Well, you can go online and say, are Smurfs real?
And those blue people.
Stop. No, it's legit.
And well, that's what I thought too. However, I can find plenty of resources telling me that Smurfs are real. The time I actually did this, the first one that popped up has changed since then, was actually a Yahoo Answers, where you ask questions and then people on Yahoo answer you. And the Yahoo answer said that Smurfs are real. So, let's see.
Whenever you answer that, can somebody like, obviously they can reply to you in the thread, but can they like personally contact you or?
No.
Okay.
No, they can't personally contact. So it looks like they've updated it now to say that they're not real. However, for a long time, they actually had up there that Smurfs were real. So you can quite literally find anything on the internet. It doesn't matter what it is. You can find some sort of reference backing you up and so forth. And I think this is actually something that needs to change in education, is the fact that no longer is it completely about reciting information back and knowing facts and things like that. It's understanding where those facts come from. And this is not the class for that. We've got more than enough to do on our plate in the chemistry class, but you should be aware of where the various information is coming from. And maybe you guys were taught that at some point. I wasn't, but that was pre-internet days. So there you go. So 3 print references. I would encourage you to go into the library to find a print reference. If you can't find a print reference, they have people in there that will help you find print references. The reference librarians are the names of them. Their whole job is to help you find information. Okay? I think that's enough of that. Everyone good with that? Okay. I have put a folder on Blackboard for the topic paper, and in that folder there is the instructions, basically what I just said and so forth, and then there's also a submit for it. When you submit it through that, it goes through the plagiarism checking. Don't plagiarize your paper. Minimum, if you get caught plagiarizing a section, would be a 0 for the paper. If, for example, and I have had people do this, I'm not kidding at all, literally copy a website and then paste it into their Word document and put their name on it. If you do that, you fail the course. It's just the way it is. So don't do it. Again, this is not something I care personally about. You're not offending me in any way, shape, or form, besides my belief in goodness between people. But it's unfair to other students. If someone else in here actually does the work to get a grade and you get the same grade by just cheating, that's not fair to the other students. And that's the reason why I care so much about it. Okay, so there's that. And that's pretty much my announcements. Do you guys have any questions about anything? Okay, there we are. So, we were doing dot diagrams and we were going to move into shapes. So let's do this as an example. Let's start out making a dot diagram. So let's do PF3. So see if you can draw the dot diagram for PF3. Okay. Everyone got their ideas for PF3?
No.
Okay. Say another 30 seconds or so. Okay, PF3. So we're going to put the P in the center, and it's going to have 1, 2, 3, 4, 5 dots around it. Okay, because it has 5 valence electrons. It's in the 5th column of the periodic table. It has 5 valence electrons. Then the fluorines are going to sit in each of the sides that needs one more. To fulfill the octets. Okay, looks like this. Does everyone agree with that? Okay, great. So that's the dot diagram. So we now know that in PF3 we have 3 single bonds, and then we have these up here, which are known as the lone pair, or known as a lone pair. You can have more than one. A lone pair there. So to find the shape, the way this shape works is it's called VESPR model, or VESPR model. But basically what that stands for is valence shell electron pair repulsion. It's a very complicated name, but you know what it means. You know what the valence shell is. That is the electrons that are on the outside of an atom, or those that participate in bonding. Electron pairs, well, that's just 2 electrons. And repulsion means that because electrons are negative, they want to be as far apart from one another as possible. Just like 2 souths, if you try and put 2 south magnets together, they push each other apart. The same thing occurs here. Because we have 1, 2, 3, 4 areas of electrons around our phosphorus, those are going to move as far apart from one another as possible. Now, what is that shape? Well, to find the shape, we're going to use this chart. And this chart is something that's going to be given to you for the exams and so forth. The only difference is the last 2 columns here are not going to be there. Because I always use those by accident in the exam. So you're going to get the first 4 columns of this chart, and you just have to use it to figure out what the shape is. So looking at the first column, the number of atoms in lone pairs around your central atom. So how many atoms do we have bound to our phosphorus here? 3, right? 3 atoms. And then the number of lone pairs is 1. So that's going to be 4 total. So looking at our chart here, it is either going to be this row, or this row. Okay, so then we just move on. The number of surrounding atoms is 3. Well, that's the only option. So the shape is going to be pyramidal. Pyramidal is the shape.
So the surrounding atoms are the F's, right?
Are the F's in this case. Yep. Yep. So it's whatever's around your central atom. So this is going to be pyramidal. And the reason why it is shown in the previous slide here. This compound is the same as this compound in terms of shape. You want your electrons to be as far apart from one another as possible. So in a 3-dimensional space, this is the arrangement that will occur that will move them as far apart from one another as it can be. Now we ignore the lone pair, and you can see it forms like a little pyramid there with 3 sides. So it's pyramidal. Here is our next one. Our next example is CCl4. I've already drawn out the dot diagram for it. Let's take a minute and see if, or half a minute, and see if we can figure out what the shape is going to be for CCl4. Okay, everyone have their ideas? Okay, so for CCl4, we have our carbon in the center, and there's 1, 2, 3, 4 atoms around the outside, and we have 0 lone pairs on our carbon. So we're only looking on the central atom here in terms of lone pairs. So there are no lone pairs on our carbon. So that's going to be 0 lone pairs. And looking at our chart, 4 atoms and 0 lone pairs is going to be the tetrahedral shape.
Will it always be, instead of just dots, X's and dots, obviously to be able to tell, or if there's, like on the test itself, would that be, would be marked that way, or?
No, it might not be.
Might not.
It might not be.
So when we do it, should we do X's and dots to separate it, or do you care?
It makes no difference to me at all.
Okay.
I can figure it out 100%. I just do that so that you can see that the 4 here comes from the carbon in case anyone's having problems drawing dot diagrams still. Yeah, I am. Yep. This chart minus the last 2 columns. The example and the shape ones are going to be cut off, but the first 4 columns will be there for you.
So we don't need to know the example of the shape. Like, for the test, we don't need to know those.
No, what I'm going to do is I'm going to give you a compound and then say, what's the shape of it?
Oh, okay.
So we're
And
not gonna
then-
draw it?
What?
Would we still draw it out? every
It's
day?
quite possible that you'll draw it.
Okay.
After we get through this, to the end, we're going to do a sample problem that I always put on the exam. And as it has like 9 steps to it, and I do that so people don't freak out when they see it's 9 steps, but it walks all the way through it. So you'll see the different types of things involved there. Tetrahedral, everyone agree with that? Okay. Finally, water is here. Let's again take 30 seconds and see if we can figure out what the shape of a water molecule is going to be. Oh, wait. See, this is why I don't put examples on the exam one. Okay. Let's go ahead and do water here. So with water, we have 2 hydrogens. So that's going to be 2 atoms. And we have 1, 2 lone pairs. So looking at our chart, if we have 2 atoms and 2 lone pairs, this is going to be the bend shape. I'm not sure why one of them is capitalized and one of them small on the chart. It really doesn't make any difference. I think it's just a typing thing. But this would be the bend shape. And as you can see, that's the example of the last bend shape there. That's why you got to take those columns off. Good with that? Okay, let's try one more. Let's start from the beginning. Actually, let's do it this way. Make sure it's not up there. Predict the shape for the compound carbon dioxide. Now, just to make sure everyone's on the right track, carbon dioxide's formula is CO2. If the dot diagram tripped you up, here is the dot diagram for CO2.
That's the only way to do it.
What?
Is that the only way to do it?
It's the only way I know of. Did you have something different? I'm assuming you did because you asked, but.
So,
I mean, I did too, like, so when you fill in the dots, like, I guess in the, I don't know, like, I don't know, it's, how is there a space? Like, aren't you supposed to fill a dot on each side before you go around for a second? 'Cause
Okay.
that's where, like.
So
that's where
this
it's
is a
possible.
simplified drawing at this point. Let me, okay, over here. So if this dot diagram tripped you up, here's the way I go about doing it. So you've got carbon, and you have 1, 2, 3, 4, okay? Then you have an oxygen here, and it has 1, 2, 3, 4, 5, 6. And then another oxygen, 1, 2, 3, 4, 5, 6. So we're going to form a bond here between these two, and then a bond here between these two. So redrawing this, trying to keep everything the same. Okay, it's going to look like this with those single bonds. Now, does this fulfill the octet rule? Okay, so if we look on the carbon, for example, we've got 1, 2, 3, 4, 5, 6 on that carbon. And on the oxygens, we have 1, 2, 3, 4, 5, 6, 7. So it's not fulfilling the octet rule there. So what we're going to need to do is make another bond. And that bond is going to be here. And then those two bound together. And then when you do that, that's going to form into this. So you've got 1, 2 bonds between these two, 1, 2 bonds between those two. You buying that?
So they're sharing.
They're sharing. Okay. Okay, does everyone have ideas for the shape then for CO2? Now, before I go to the chart, let's just think about this. We've got one area of electrons, 2 areas of electrons. So if you have 2 areas of electrons, they want to move as far apart from one another as possible. How far apart is that going to be? If you have 360 degrees all the way around, they're going to go opposite each other, right? That's what they're going to do. So when we look up here then, 2 atoms surrounding 0 lone pairs, that's going to be a linear shape. They're going to be pointed at exactly opposite directions, which is linear.
Wait, why do they have 0 lone pairs?
Yeah.
Because
Okay.
oxygen has 2, well, both oxygens have 2 lone pairs.
Correct. We are only looking on the central atom.
Oh, okay.
do
Oh, so let's.
Only always look at the central atom.
Okay.
The way that you know this is going to be true, okay, first off, it's true. If you forget, we would have 2 atoms and 4 lone pairs. If you look at the chart, there are no options that have 4 lone pairs there. It's just not a possibility. There's too many things around the middle, actually. So you only look at that central atom. Yeah.
This might be a dumb question, but what, once again, defines the lone pair?
A lone pair is a pair of electrons that's not being shared between 2 atoms. So in our drawings, there are the ones that are not between the 2 atoms. So for example here, this one doesn't have another atom above it, so this is a lone pair there. Okay, let's do one more. Let's do PSCl. PSCl. And this is pretty much going to throw everything we just been doing into one problem here. Okay, let's say 30, 40 seconds for the dot diagram part. Okay. Does everyone have their dot diagram at least, or their idea? Okay. So here we are then, we're going to put our P in the center. And it's going to have 1, 2, 3, 4, 5 valence electrons around it. Then we may as well put in the S next. S has 6, so 1, 2, 3, 4, 5, 6. And we're going to form a bond here. Now, looking at that, that's going to give 1, 2, 3, 4, 5, 6, 7 for the sulfur. 1, 2, 3, 4, 5, 6 for the phosphorus. So we'll make another bond there to fulfill the octet of the sulfur. So 1, 2, 3, 4, 5, 6, 7, 8 for the sulfur there. P is not happy yet because it has 1, 2, 3, 4, 5, 6, 7. But thankfully, we've got another chlorine to bring in here to fulfill that octet. Does that make sense?
So if you were to draw that like cleanly, how would it look? I'm just curious.
No, absolutely. plan on doing so. Let's draw. So we've got sulfur. Oops. Okay. Any other questions about the dot diagram? Yeah.
Could it be, okay, you see how above P is 2 X's?
Mhm.
Could it be 1 X above and 2 X below? Would it make a difference or? would it be
Um,
wrong?
I wouldn't count that as wrong from a dot diagram point of view. It may be a little confusing when you think of a lone pair.
When I think of low pair, I think of 2 together though.
Yeah, because you think of two together. So if
So-
you were to separate them, I wouldn't count it as wrong,
But it would be a lone pair anymore.
but you would have to recognize that it's still a lone pair. Because you've got two of them all on their lonesome.
Yeah, okay, I see what
So-
you're saying. Okay.
Yeah, I guess that would be a way to think of it. Yeah.
On the exam, are you gonna want us to like circle it like that, like where we're forming bonds?
No, don't care. I mean, it may be helpful to you to keep track of the number of bonds and stuff, but yeah, I'm happy if you draw the dot diagram in any way, shape, or form. So the cosmetic things I add and so forth, great if you do, but by no means do you have to. I like those questions because that means you probably got your dot diagrams right. Okay, good. So here we are then to figure out the shape. We have, does anyone need more time to figure out the shape? I think the dot diagram went okay. So, okay, we have 1, 2 atoms bound to our central phosphorus. We have 1 lone pair. So if we have 2 atoms and 1 lone pair, that is going to be the bent shape. The bent shape.
When you're looking to decide what shape it is, you don't use your central outside of looking at lone pairs. Like for the one we just did, it's not 3 atoms, it's just 2. You didn't count the central.
Yeah, no, you don't count the center, because it's the number of atoms around the central. So in this, like, yeah. Okay. Does everyone else understand where the bent shape comes from? Okay. Well, this one's about as difficult as it gets, because it's got three atoms with a double bond, a lone pair, and then a single bond as well. It's kind of difficult to get more complex than that. So if you did good with that one, you should be in pretty good shape. There will be some that trip you up from time to time, of course. I still get tripped up all the time. But you should be on the right track. So that's the shape of these things. So when, for example, carbon tetrachloride is a molecule, it's going to have a tetrahedral shape. Carbon dioxide is a linear shape. And because of these shapes, they have properties associated with them. For example, carbon tetrachloride used to be used in dry cleaning. When your clothes get dirty and stuff, it's oils from your skin that makes them dirty for the most part. And because of that, you need something that will interact with the oils to clean them. And carbon tetrachloride will do that because of its shape. The same thing with oil and vinegar salad dressing. What do you always have to do with that salad dressing before you use it?
Shake it.
Shake it up, right? And the reason is because the oil and the vinegar don't mix. So in chemistry, to explain that role of what mixes and what doesn't mix, we have to understand something called polarity. And polarity is simply the unequal sharing of electrons. It means that one area of your molecule has more electrons than something else. And there's a lot of different ways for chemists to describe polarity depending on how exact you want to be. For this class, we don't really care about being exact, so we're going to use a very simple rule of thumb. Let me get a little space here to draw right on the board. Something is polar if it has lone pairs on your central atom. So polar So if your molecule has lone pairs on the central atom, then it's going to be polar. The other form of it is called nonpolar. And this would be the opposite. No lone pairs. On your central atom. So you need to look at your dot diagram. If you have lone pairs on your central atom, then you know that it's going to be a polar molecule. If you don't have lone pairs, then you know it's going to be a nonpolar molecule. Now, some of you would have learned about this in high school, I know, and this does not always hold true, but for this course, this will always hold true. And I'll make sure the examples work this way. So you can very quickly see whether it's polar or nonpolar. Why do you care about this? Well, you care about it because in chemistry, there is a rule that like dissolves like. So that means polar things are going to dissolve in polar things. So water is polar. So polar things are going to dissolve in water. Nonpolar things will not dissolve in water. And water is the only thing I'll ask you about, is whether or not something will dissolve. It's the primary liquid used to dissolve things throughout the world, so it's the only one I'm going to care about here. And we know examples of this, whether we know it or not. So for example, oil and vinegar salad dressing. The vinegar is polar, the oil is nonpolar. So they don't dissolve in each other. And that's why they constantly are separating. When we have an oil spill, say the Gulf of Mexico, and there's an oil spill in the Gulf of Mexico. The oil is nonpolar. Okay. Water is polar, so that's why the oil sits on the top. Very little of the oil actually gets dissolved in to the water. So we can go through with skimmers and just collect it off the top and grab the bulk of it. It doesn't get it all by any means, but it does a good job. Just because it doesn't dissolve in it. Vitamins, for example. Certain vitamins in your body aren't going to stay in your body very long if you take them because they dissolve in water. So when you take vitamins, for example, 90% of the vitamins are water soluble, which means they dissolve in water and they just travel through your body as waste because of it. And it all comes down to whether or not something is polar or nonpolar. So looking at our examples up here on the board, PF3. Is PF3 going to be polar or nonpolar? Polar. Does everyone agree with that? It is indeed polar. So will PF3 dissolve in water?
Yes.
Yes, it will. It will dissolve in water. Another example of something that will dissolve in water is sugar. Sugar is polar. And we know sugar will dissolve in water because of that fact. CO2, carbon dioxide. Is carbon dioxide polar or nonpolar?
Nonpolar.
Nonpolar. So will carbon dioxide dissolve in water? No, it won't. This is actually very common in the world that we live in. An example where carbon dioxide does not dissolve in water. Does anyone know what that would be? Soda. Okay. That's the way we carbonate drinks.
Sorry, I don't know if I like this what you guys know.
Okay.
Why is it nonpolar again? You
Okay.
said that the CO2 is nonpolar?
CO2 is nonpolar. And the reason it's nonpolar is because in your central carbon we do not have any lone pairs. Okay? So So no lone pairs means nonpolar. Sodas and stuff that we drink, anything carbonated, the way that they carbonate it is they put carbon dioxide into it, and then when you open it, the bubbles come up, right? You're familiar with that? Those bubbles are CO2 escaping out from the pressure of being trapped in the water, because they're not dissolving in there. And that's the reason why, is because CO2 is nonpolar, so it doesn't dissolve in water. Carbon tetrachloride is nonpolar, therefore it won't dissolve in water either. It does dissolve in oils and so forth, but not in water. So this is one example of a property that shape takes part in. Yeah?
This might be slightly off subject, but is that why
Okay.
like if you shape the top of it one level and open it like upside?
It goes crazy. Yep. So what's happening there is when you shake it, you're adding energy into it, and that energy is being used by the carbon dioxide to escape out of the liquid. And that's why when you open it, it gives it a way to release that pressure, and then it goes out. It's the same thing as if you leave a can of soda in your car in the summertime. The sunlight hits it, and that energy allows the CO2 to escape, and then on a warm enough day, it will just pop through the can because of the same thing.
Once again, not totally on top of it. So
Okay.
what is if you put, like you've seen these experiments before, where they put like a Mentos,
Mhm.
what's in that makes it interact?
So the Mentos and Diet Coke phenomenon, or Coke, I forget what it is. The reason why that works is not so much adding energy to get the bubbles to form. It gives the Mentos acts as a place for the bubbles to form. Because the Mentos surface is rough, bubbles can form easily on it. So for less energy, the CO2 can escape quicker, and that's why you see all of a sudden this huge output of it. Because of the fact that the Mentos allows for those bubbles to form.
It's off topic, but
It's
it
okay.
kind of relates to like the whole soft drink in a hot
Yeah.
bar. If heat's giving it energy, doesn't the cold slow it down? So when you put like a soft drink in a freezer and it explodes, why does that happen?
Okay. First, let me say that's very good thinking there, by the way. It's a different mechanism. So water is one of the very, very unique substances on Earth that when it forms a solid, it actually is less dense than as a liquid. I can't even imagine how rare it is, but it's the only one I know of. So what happens is you've got your can, and when you freeze it, to get less dense, the liquid actually has to expand. But it can't expand anywhere because the can is full, and that expansion of the ice is actually what breaks it. Growing up in Iowa, oftentimes in the wintertime you have to go outside and put like styrofoam wrapping around pipes and stuff, because what will happen is if a little bit of water is left in those pipes and then it freezes, it'll actually break pipes and so forth. Like cast iron pipes and things will just blow apart without any problem because of that. And that's because of the water going from a liquid to a solid, it's got to expand. And that's just the way it is. Now, we're very lucky water does that, because the hydrothermal cycle of the Earth wouldn't exist without it. So if you think of it this way, icebergs. So icebergs float, but if they actually sank to the bottom where it was colder, they would never turn back to water again, and you wouldn't have this cycle between solids and liquids, because they would just go to the bottom and then sink. So our Earth wouldn't be the way that it is if it wasn't for that fact. No one ever really thinks about that, but it's an amazing, amazing thing of water, because it does that. So. Yep. But yeah, that's why. It's just a different mechanism. But you're absolutely right. You can blow up a can of soda in your car if it's too hot or if it's too cold. So, I've had that happen to me many times. It's ugly.
Is this kind of what you were referring to earlier with the 9-step process, that we would theoretically start with something and then we're just
Yeah.
continuing to add all these?
Yeah, so Let's do that problem. It's time for that now anyway. There are other properties that are controlled by shape, things such as melting points, boiling points, these types of things, but again, we're not really going to get into them. The only one I really care about for now is this idea of whether or not it dissolves in water. So just for completeness, ionic compounds will generally dissolve in water, and polar covalent compounds will dissolve in water as you're going through it. Okay. So as promised, I want to do a sample problem that I put on the exams. I've always put on the exams. So I haven't written the exam yet, but I can guarantee you I'll put it on there. And I want you guys to see it so you don't freak out about it all at once.
Did you say polar covalent bonds?
Polar covalent. So if you have a covalent molecule, like all of them we just drew were all covalent, then if it's polar, it will dissolve in water. Any other questions about that?
Could you just repeat those two again? You said ionic compounds will dissolve water, polar covalent.
Will dissolve in water. And there are exceptions to that, but yeah, we don't particularly care about it. So I just don't like lying to you guys point blank. I know it's an intro class and everything, but I just, in my heart, I don't like it. So, okay. Consider the compound sulfur dichloride. Okay, so question A. Oops. I guess okay, draw the dot diagram for elemental sulfur and chlorine. So this is elements by themselves, not in a compound. Okay, the dot diagrams for the elemental forms, sulfur is going to be an S. And how many dots am I going to put around my sulfur?
6.
6. Chlorine is a Cl, and it's going to have 7 dots around it. Next, is the compound sulfur dichloride ionic or covalent?
Covalent. No. Yeah, covalent. Physical formula.
Okay, let's vote. How many people think sulfur dichloride is ionic? And how many people think it's covalent? How many people don't want to vote? Okay. Now, the way that we know this, there's actually 2 ways to know it in this problem. The first and best way is by looking sulfur and chloride is chlorine. Those are both nonmetals. Since they are both nonmetals, that means that this is going to be a covalent compound. The other way to know it is the fact that in the name, you have the prefix di, and we only use di or the prefixes for covalent compounds. So either way is going to tell you that it is indeed a covalent compound. Let's see. what is the formula of sulfur dichloride and the dot diagram? So on your paper, see if you can come up with what the formula of sulfur dichloride is. And once you've got the formula, then draw the dot diagram for it. Okay. Okay, the formula for sulfur dichloride. Anyone want to share what they got? Go ahead.
SCO2.
SCl2, perfect. And the dot diagram is going to be your sulfur with 6 electrons like before, and then a chlorine on either side.
So then it has two lone pairs?
You're jumping ahead, but yes, it does.
Okay.
But do you guys see how this problem's going? It's walking us through all the steps of chapter 4. At the very beginning, what's a dot diagram? Then talking about ionic versus covalent, the naming of it, the dot diagram for the product, D, I guess in this case, is how many lone pairs and bound atoms are on the central atom. And then what is the shape? Okay, everyone good with the shape? Okay, so how many lone pairs are there? There are 2. How many atoms?
2.
2 as well. So going to our handy dandy chart, 2 surrounding atoms, 2 lone pairs is going to be the vent shape. I always make the joke that if you don't know what to guess, guess that, because you got twice as likely. Yeah.
Where was the second pair at again over here? So that you're on top?
So you have 1 lone pair right here, and 1 lone pair right there. Okay, anyone else have questions about the dot diagram there? Okay. F. Is the compound polar? And will it dissolve in water? Take 30 seconds or so. Okay. Is SCl2 polar or non-polar?
Polar.
Polar. It has the lone pairs on the central atom, so it's polar. And then will it dissolve in water? It is polar, so the answer is yes. Because water is polar as well. It's the real reason why. They're the same shape, actually. Okay, does that make sense? Walking through it. Okay. So you will see a problem like that on the exam. If you go to Blackboard, let's see, and we go to practice problems, the third one down right here is chapter 4 and 5 practice problems. And if you click on it, let's open it up. Zoom in some. I have 2 problems here. Where's my pointer? That runs through these various things. So we've done this first part. This is chapter 4. This is chapter 5. So if you want, you can take a look at these and run through the chapter 4 material, which is there, and then there. So consider the compound nitrogen trichloride, ionic covalent formula, valence dot, bonding, and then shape as you go through it. So it's a couple more practice problems for you. Questions about that? No? Okay, so now we have 7 minutes left. I'm going to let you guys decide. I know what the answer is. Do you want to go on to the new chapter or just call it here for the day?
Call it a day.
A couple of students in yesterday's class complained I stopped a little early, so I wanted to ask. Yeah.
I know it's a little bit too early to
Yeah.
talk about that.
Sure. I don't remember where we stopped the old one at. I think it was at the end of the last chapter. So I think all of chapter 4 will be on there for sure. Chapter 5, we'll have to see how far we get. I would expect a large chunk of it to be on it. So probably through balancing equations is what I would aim for. But we'll have to see. Ooh. I think that was all in the old one. I need to double check that, but I don't think there'll be any chapter 3 on it. Okay. See you later. Go before I injure somebody. Yeah.
Okay, so I found something I wanted to use looking on. And it's really cool, but because it's not out.
Go for it. I'll help you find information if you need it. That sounds awesome, actually.
I was really impressed.
Yeah, no, that's cool.
So with the process, so like obviously I feel pretty good about it.
Okay.
So like along the way, it'll be like if we got A, B, C, would it be points off if we missed D or E? Like
Yeah, so like for example, if you missed D, and you said that you had 3 atoms in one lone pair,
Right.
but then you use that correctly later,
Okay.
then you'll get points for it.
Continue to follow suit then. Okay.
Yeah. So after you make a mistake, I will base your answers on your mistake or the correct answer.
Okay.
So you can get either way, you can end up getting points for it that way.
cross section makes a lot of sense. Like the more you add to it, like when you show it together, you now can go backwards.
Exactly,
You're
yeah.
like, wait a minute, I got it here, but I need to go back to here because I understand how I got from there to there.
Okay, good.
So-
Yeah. I like it a lot because, like, on an exam, I can quite easily just say, what is the shape of this? And have that be a question. But if you make a mistake there, I don't know where the mistake is, and it's really hard for me to get partial credit and so
You
forth.
can go backwards.
Where if I start with the very beginning and the easy stuff, I can get points for it, but also I can give partial credit because I know where you made the mistake.
Yep.
So there will be some like shape, like what is that, but then, it's a good question.
I actually like the multi-step because you actually can go back and check your work.
Yeah, no, that's true.
Great.